So this question gives a rod with length L and uniform charge density lambda. The question is find the electric potential at point A, which is a distance A, away from the end of the rod. So that's what we're trying to find. Let's remember that the potential at point A is going to be the integral of a little bit of potential made by a little bit of charge dq. So the integral of k times dq over r. Let's think, what do we mean by dq? What do we mean by r? dq is our little bit of charge along the rod. So here's our dq. Typically we write dq in terms of the length, so it's going to be the amount of charge on a little bit of length is going to be the density times the little bit of length. Because we have a horizontal rod, we'll pick a horizontal length dx. R is our distance from our point to our charge. So this distance right here is r. And we see that r is also from the origin in the x direction, so r could also be written as x. So here's where x equals 0, here's dq, that distance is r, and it could also be written down as x. So we'll add that here as well. So let's put in our dq and our r into our expression for v. So v is the integral of k times dq, which is lambda times dx, divided by r, but r is the same thing as x. When we do our integral, we can take our constants out front, so we get k times lambda times the integral of dx over x. We want to be sure we put in the limits of our integral, so we integrate from one end of the rod to the other end of the rod. So we want to integrate over the object that's carrying the charge. This end of the rod is x initial, has a value of a. This end of the rod is x final, equals the entire length of the rod plus a. So we're doing our integral k lambda outside the integral from x initial, which is a, to x final, L plus a, of dx over x. So there's our expression. You might remember that the integral of 1 over x dx is the natural log of x. So we get k times lambda times the natural log of x. That's going to be evaluated at L plus a and a. So we put in our limits. We get the natural log of L plus a minus the natural log of a. And we remember if we subtract two natural logs, that's the same as taking the natural log of the two arguments divided. So that would be k times the natural log of L plus a divided by a. So there's the electric potential at point A at some distance from the end of the rod on axis.